Hello everyone, I'm doing a presentation on redshift and blueshift, which is just an application of Doppler's effect. So by the end of this video you'll get an intuitive understanding of what redshift and blueshift, what they actually are. Now I won't be going into the mathematics of it, I won't be going into the derivation of the formulae. I just want you to have an intuitive understanding of how redshift and blueshift happens and what exactly is the Doppler's effect. Firstly, let's start with some questions. Now, these questions, they're very important questions. I mean, existential questions. I'm sure humans have had these questions ever since we gained consciousness. Like, how old is the universe? Does it have a fixed size? And how are we going to find these answers? Well, science has made it possible for us to know the answers to these questions, and we'll be discussing how. So, firstly, you need to have a prerequisite understanding of the visible spectrum, visible spectrum of light. Now, the thing is, light travels in the form of waves. Like ripples in a pond, light is actually, you can think of light as ripples within the electromagnetic field. So, there is an electromagnetic field that permeates throughout the universe, and light is just the vibration of those fields perpendicular to each other. So light is just a wave, and what we perceive as colors, what our brain perceives as colors, is actually light of different wavelengths. Like violet light is the light which has the shortest wavelength and therefore the highest frequency. Red light has the longest wavelength and the shortest frequency. So remember this: red light has the longest wavelength and violet light has the shortest wavelength. It will be needed to understand how the redshift and blue shift happens. Okay, so now we know about the visible spectrum and the fact that light is a wave, which is not exactly 100% correct, but that's another thing. Now, let's look at something called the Doppler's effect. Now, Doppler's effect is actually an apparent change in frequency of a wave caused due to relative motion between the source and the observer. There are these animations here which I pulled from Wikipedia, and you can look at this red thing, that's the source. On the right side of the screen you can see that this source is emanating waves, and these waves appear to have the same wavelength to both the observers, the observer on the left and the observer on the right. So this they perceive the wave to have the same wavelength. Now, if this was an electromagnetic wave, then they would think of it as the same color as long as it fell within the visible range. So they would both see it as the same color. But on the left, you can see the source is in motion. Now, as you can see in the animation, when the source moves towards the observer, the waves get squished together. The waves get squished together, and because of that, the observer on the right sees an apparent change in the wavelength, and to the observer on the right, the wave appears to have a shorter wavelength. So this is what we call the blue shift. Light is blue shifted for the observer on the right, because for the observer on the right the wavelength decreased. Similarly, as the source is moving away from the observer on the left over here, the wavelength appears to be longer to the observer on the left. So the wavelets, they appear to be spread far apart. Now this is called the redshift. When the source moves away from the observer thinks that the light is actually red. So that was about the Doppler's effect. Now we know Doppler's effect, and we know that light is a wave. And Doppler's effect, it applies to all waves. Okay, as long as there is a relative motion between source and observer. Now, combining these two information that we have just learned, it is therefore logical to conclude that light should also get its wavelength shifted, and that's what becomes the red shift and the blue shift. When a wave is at rest, let's say that light wave is green in color. I'm saying green because it's close to between blue and red. So if it appears to be green light at rest, then it gets red shifted and becomes red if the source is moving away from the observer, or even if observer is moving away from the source. when they are moving away from each other, the wave appears to be redshifted. When they are moving towards each other, the wave appears to be blue shifted because it gets squished together. The crests and the troughs get squished together. When it's blue shifted, they get split far apart when it's red shifted. So that was about the Doppler's effect. And using this knowledge of the Doppler's effect and about redshift and blue shift, we can conclude many things using astronomical observations. That's what we do in science. Like we make up a hypothesis and compare it with observation. So we observe that objects moving towards us appear blue shifted. When this galaxy moves towards us, it's blue shifted. When objects move away from us, they appear red shifted. Now when it moves away from us, it's red shifted. It gets blue shifted when it's moving towards the Earth, red shifted when it moves away from the Earth. So that was about redshift and blue shift, and using this knowledge of the Doppler shift, we can also determine the velocity of the object that we're observing, of the astronomical object that we're observing. We can not just determine the direction of the movement of the object, whether it's moving towards us or away from us, but we can also determine the velocity with which it is moving towards us or the velocity with which it is moving away from us. Well, the greater the velocity, the greater the shift. Now that's basically it, and we can do it by comparing it with, now when you're looking at a star, suppose you're looking at a star using a telescope and you find it to be slightly blue shifted, and now you want to find with what velocity is it moving towards us. It's blue shifted, so it's moving towards us. Now to do this, we compare the light we get from the sun with that we get from the star, because the sun is almost stationary with respect to the earth. So we can use it as a reference. We can use light emitted by the sun as a reference and compare it with the light that we get from the stars, and by using the shift between these two data we can determine the velocity with which the star is moving towards us or with which it is moving away from us. And the thing is, when astronomers using using telescopes of high power that can even observe galaxies, when they looked at the stars, they found that 90% of all galaxies are observed to be redshifted. This is a huge discovery. So 90% of all galaxies are redshifted. It means 90% of all galaxies are moving away from us. Most galaxies are moving away from us. Only the ones that are nearby to us, that are nearby enough for gravity to pull us together, are the ones coming towards us. But most of the galaxies are moving away from us. Since most of them are moving away from us, we can say that the universe is expanding. You know, like you can think of it, imagine like a balloon. Like the universe is a balloon and you're blowing air into the balloon, so it's expanding, and because of that, within the universe the distance between us and the galaxies is increasing. So they appear to move away from us, but they're not exactly moving away from us. Actually, the space between us is what's expanding, because of which it appears that they're moving away from us, or from their perspective we're moving away from them. Perspective is a weird thing. So that's how we know that the universe is expanding. And we can also find the velocity at which galaxies are receding using the Doppler shift equation, the mathematics of which I'm not discussing in this video. They're receding away from us using the difference in wavelength by comparing with the sun. We find the difference in wavelength, and using Doppler shift equation we can find the velocity with which they are moving away from us. And again, it is found that farther the galaxies are, the farther they are receding from us. Thus, the universe is not just expanding, it is expanding at an accelerating rate. And then, through mathematical calculations, mathematical modeling, we can conclude that the universe is 13.6 billion years old or 13.8 billion years old. That's plus minus 0.2 billion years. So that's how old the universe is, guys. And now we know that because of our knowledge of Doppler shift and using mathematics and the fact that light is a wave but not actually a wave. So that was all. Thank you.